Okay, so your next Achieve homework is posted. I just posted it, and it's due on Monday, so it'll cover content that we cover today and Friday. We'll hopefully finish chapter 1 on Friday. We'll start chapter 2 on Monday. Generally, Achieves will be due Mondays at 9 a.m., except for any changes that might have to happen, but I'll let you all know in class and in a Blackboard announcement if that's going to change, but you can expect Achieve homeworks due Monday mornings from now on. Okay, so I looked through survey results. For office hours, there wasn't a different time that worked for most people, most students, so I'm going to keep the Monday, Wednesday 1 to 1:50. I know this doesn't work for everybody, but we do have two other things. There's recitation, which is essentially an online office hour where I'm there to help you work through problems, answer questions, things like that. And then if you are able to come to those and you still have questions, or if you can't come to my office hours, send me an email and we can find another time to meet to review homework or, again, answer whatever questions you have. I will talk about other survey results in future classes, but one that I wanted to talk about today was my question about what concerns do you have about our class? And I have a lot of concerns that I'm going to show you on the board, and my goal here is not at all to minimize your concerns about the class, but rather to show you that a lot of your concerns are shared across many students. So I'll show you some of them. Some were like falling behind or failing, losing track of assignment due dates, just worried about the course load. Some students said they struggled in AP Chem. These are individual responses. Chemistry isn't my strong subject. I've struggled with chemistry in the past. Falling behind if I don't understand something. It's been 3 years since I took chemistry. I didn't have a proper chemistry class because of COVID. Chem in high school was interrupted by COVID. I took chemistry online during COVID. I took chemistry during COVID. Not remembering things from high school, understanding concepts in general. I did not take AP Chem. I have a hard time with calculations and equations. So these are only a few concerns. There are many more. I posted a lot of the common ones, but there were still others that are shared across many students. But my goal here is to show you that if you have a concern in the class, you're not the only person with that concern. I understand that many of you took chemistry during COVID, or it's been a while since you took chemistry, and that's fine. That's why we're starting from the beginning. And I'm doing my best to explain all of chemistry, all of Gen Chem 1 as best I can. But as a college student, it's also your responsibility to ensure that you're understanding the majority of these concepts. And if you do find yourself falling behind or losing track and things like that, you have a lot of resources to help you out. There's your classmates, so you all have the same assignments, you all have the same due dates, so you can keep each other accountable. You can come to me, email me, come to office hours. There's also tutoring services through Detroit Mercy. Maybe using a specific calendar will be helpful for you to remember all of the things that are due, things like that. There are a lot of different ways to accommodate any of the struggles that you're experiencing. And if you don't identify with any of these struggles, then great. When we're working on practice questions and you're understanding them and the person next to you isn't, then you're in a good situation or a good place to then help the person next to you. That then helps them learn what they're struggling with, and it solidifies what you understand, because having to explain something will help you remember that content as well. All right, we're going on to significant digits, but are there any questions before we get started with the chemistry? Yes. So these are the lecture notes. In a few slides, I'll let you know when we start an iClicker question, and a question will be pushed to your devices for you to answer them on your devices. And I'll explain that when we get there. But these are just our lecture notes for now. All right, when we're communicating measurements or values in chemistry, how precise that value is matters. So we use significant digits, which are also called significant figures, which you'll see in our slides. Which are also called sig figs for short. So anytime you see significant digits, significant figures, or sig figs, that's all the same thing. And so depending on what you're measuring or what values you're adding together, multiplying together, subtracting, dividing, your end value has a specific number of significant digits. And so our goal with this unit is to determine the correct number of digits to indicate the precision of a measurement or calculated result. Oh, hold on. There we go. Okay. Okay, but before we talk about that, we're going to talk about scientific notation. We'll use scientific notation to communicate very large or very small numbers. Some examples of really large and really small numbers is the width of a red blood cell. That's 0.000007 meters, or in scientific notation, 7 times 10 to the negative 6 meters. When we use scientific notation, we have our non-zero number multiplied by 10 to some exponent, and that exponent tells us how small or how large that number is. There are over 20 trillion red blood cells in the human body. Again, this is many zeros to record. It's not immediately clear how large that number is. And so using 10 to the 13 for that number, it would be easier to compare to a number that's similar in size. So when we are writing numbers in scientific notation, we have a coefficient, and then we have it multiplied by 10 to a certain power. So 2.36 times 10 to the negative, or to the fifth, that is an example of a number written in scientific notation. The 2.36 is the coefficient. And then 10 to the power of 5 is the part where we say which power we are raising 10 to. Another example, 1.4 times 10 to the negative fourth. 1.4 is the coefficient. And then power of 10. So that's what scientific notation looks like. And then let's look at these examples down here. It's the same numbers written in scientific notation and then not in scientific notation. So when you have a number that's not in scientific notation, to convert it, you always place the decimal point after the first digit that's not 0. So in this case, we would move our decimal point to be between the 2 and the 3. And then we have to count how many places are we moving the decimal point. In this case, we're moving at 1, 2, 3, 4, 5. 5 units. So we have our 5 as the exponent. So here we're going 5 spaces left. If we're communicating a large number greater than 1, then our exponent is greater than 1. It's a positive number. If we're communicating a small number that's less than 1, 0.00100014, then we use a negative exponent, because here, to get our decimal point after the first non-zero digit, we have to go to the right. So we go to the right 4 places. So we have 1.4 times 10 to the negative 4. So numbers greater than 1 have a positive exponent for 10. Numbers less than 1 that are decimals have a negative exponent for 10. So a bunch of practice in the Achieve homework, and we'll do some more in here as well. Before I move on, questions about scientific notation? Okay. So here's an example where significant figures are important. We can use scales or balances to measure mass. A balance at the deli counter, where you order lunch meat or cheese or something like that, these balances are rough balances. They might measure up to 1 gram, maybe 0.1 or 0.01 grams, and that's about as precise as they get. If you're using a balance in the chemistry lab or biology lab or research lab, you can obtain the mass to a larger number of decimal places. So that means, here's an example here. That means that with this scale, you're getting a much more precise measurement of whatever you're measuring than you would if you used a scale like this that only goes to the whole number or 1 or 2 decimal places. And so this is why significant figures is important, is because depending on how many significant figures are in a number in a measurement that you're communicating, that communicates how precise that measurement is, how much you had to estimate what that value is. So significant figures indicate the precision of a measurement. I keep trying to say membership. The precision of a measurement. So we're usually communicating measurements in science. So the correct number of significant figures in those measurements has to be determined. And your calculator often doesn't provide the correct number of significant figures. We'll do examples, but the best process is to carry out as many figures, significant or not, as possible until you're completely done with the calculation, and then determine how many sig figs should be in your answer and round at that point. All right, I have a few slides where we're just talking about what is considered significant, what's not, and then we'll go through examples. So this next slide, I don't think you have anything to write down, but you can just read and listen. This slide just outlines which numbers are significant, which ones are not. Any non-zero number, this is the easy rule, anything that's not 0, that's always significant, no matter where it is in your number, always significant. So number 54, we have 2 significant figures in that number. The 5 and the 4 are both significant. Now the rest are all about zeros. So this is where it can get tricky, but with practice and everything, hopefully it will become more clear and intuitive. So if you ever have zeros between significant numbers, like 504, that 0 is significant. So we count that as a significant digit. 504 has 3 significant figures, the 5, the 0, and the 4. If you have any zeros that are left of non-zero digits, those are not significant. So 0.00504, only the 5 and the 0 and the 4 at the end are significant. Everything before that is not significant. And then the second example, we never write numbers this way, but if you ever see a number where there's zeros without a decimal place before non-zero numbers, those zeros are not significant. I don't think we'll come across any examples like that. But if you do, those are not significant. If you have a number greater than 1 and a decimal point, all zeros to the right of the decimal point are significant. So this is where, if you think about the scales, if a scale can measure up to 3 decimal points, then that's telling us a very precise measurement, as opposed to just the number 2, then we don't know if, like, how precise it is after that. So having zeros after the decimal, those are considered significant. And then for trailing zeros, these are not significant unless we have a decimal point or we're using scientific notation. So this first example, 4,200, there's no decimal point there. So we can say the 4 and the 2 are significant, but not the 2 zeros. But if we place a decimal point at the end, then these 2 zeros become significant because this implies that this value is now precise up to that decimal place. Whereas here that's not implied. So all of these are significant, all 4. And then in scientific notation, any number that's multiplied by the 10 to some power, all 3 of those, or any of those digits are significant, as long as it's after the decimal. Okay. Questions on these?
What if it's only 4.20 without the times 10 to the third? Is that significant too?
That would be significant too. So if we don't have 10 to the third here, but we have 4.20, that's like this room here. So numbers greater than 1, everything to the right of the decimal point is significant. So this would still be 3. Other questions? Okay, so this is identifying which digits are significant. The next slide is if we're doing operations, addition, subtraction, or multiplication and division, then how do we determine how many significant figures are in the answer? For addition and subtraction, we find the lowest number of places where we have a significant digit. For that first example where we have 0.24, that number is significant to the 100th place, where the 4 is. The second value is significant up to the 1,000th place, 0.345, so that 5 is significant. But we have to use the lowest place, so our answer that's reported is in only up to the 100th place, so we can only use 2 decimals there. In the second example, the first number is significant to the ones. That 3 at the end is considered significant. But the second number is significant to the 100th, that 3. So in our answer, we can only report significant digits to the 100th place. So essentially, the least precise number that you're adding or subtracting, wherever that place is where the significant digits end, that's what is in the answer. For multiplication and division, you look at what you're multiplying or dividing, identify number of significant figures in all of those numbers, and the lowest number of significant figures is what you report in your answer. So in the first example, we have 2 significant figures for 23, 3 significant figures for 436. In the answer, we report 2 significant figures because of the 23. For the second one, we have 3 sig figs, 2 sig figs, so in our answer, 2 sig figs. Doesn't matter where the decimals are. We can only report total number of sig figs. So I mentioned earlier some rounding is required, but always round at the end of your calculation. in the table that's coming up in a few slides, we'll get some practice doing that. All right, now questions? Okay. One more slide on addition and subtraction, one more slide on multiplication and division, and then we have practice. All right, so to reiterate, in calculations involving addition and subtraction, the number of decimal places in the answer is rounded to the number of decimal places as the measurement with the fewest number of decimal places. So if we're adding these three values together, we have 3 decimal places in the first number, 2 in the second, and then 1 in the last number. So in the final answer, if you were to add all of these together in your calculator, you'll have more digits. But if we're following significant figures, we have to report just to that 1 decimal place, because that's the lowest decimal place that's present in that calculation. And then for multiplication and division, the number of sig figs in the answer is the same number of sig figs in the measurement with the fewest sig figs. So here we have, if you trace this down, we have 34.2, that's 3 sig figs, 1.989, 4 sig figs, 0.25 is 2 sig figs. That's the lowest number of sig figs in anything that we're multiplying or dividing. So our answer can only have 2 sig figs. So in this case, it will be 200. Okay, I remember from 9 a.m. that you all have all of these values already. So work on filling out the rest of this table. Some of these squares are going to end up being the iClicker question. So I'll give you a minute to work on it, and then I'll push those questions to your devices. So looking at these calculations, identify the number of sig figs that should be in your answer, and then round the calculated answer with that correct number of sig figs to get the final answer. And then if you're having trouble with iClicker, this is a good time to let me know so I can, you should all be able to join the class. So it says out here your instructions started correctly. And then let me actually just start. So I'm just going to start the questions. It should push to your devices, and then if you're not getting these questions, let me know. What we'll do, this is my first time using iClicker, so I have to adjust how I'm going to do it in the next class. You should get 3 questions. What I want to do in the future is give you all 1 question at a time so I can collect all your answers and then review the question. But obviously it didn't work that way for this iClicker. So what we'll do is you have access to all 3. You can answer all 3. We're going to go over the first 2. And then before we go over the last one, I'll close the quiz. So you just want to make sure that you have all of them submitted before I close it. And I can see how many have submitted at the top, so I'll remind you all. Yeah. If they're, yes, or you can just. So usually for 16 for scientific notation, we use it. Sometimes you see it like in drawings. Not really sure how or why. If there are matches.
Okay, thank you.
Oh. Yeah. Yeah, that's like around.
Yes, we know the lowest decimal range, which is for the calculation. Because I'm using the answer, we report up to the tens place in the decimal. So you have 45. So that's in the answer, there's because of the 45. No, because it's adding and subtracting, we report the least precise number, but anything before that is zero. So yeah, that's the difference in like adding and subtracting. Adding and subtracting, you just report the least precise number. So the or the tens place, but you still need to work. Okay. Okay. You all can probably see I messed up on formatting. You can see the answer if you go to the next question. But let's talk about why these are the answers. So in the first question, how many sig figs are in the final answer? 3. And then can someone explain why it's 3?
Because 22 is the lowest decimal place is in the tens place, and so when you round, it's going to be 45.6, and that would be 3.
Thank you. So we see that we're adding something with 3 digits past the decimal and something with 1 digit past the decimal. So in the final answer, we can only report up to 1 digit past the decimal, which is this digit here. But we still have the 45. So we round up since it's 45.59, and our final answer is 45.6 with 3 sig figs there. Remember, that's the rule for addition and subtraction is we report to the least significant place. So in this case, it's the tenths place past the decimal. All right, how about the second one, the second row? How many sig figs? 1, and then why is it 1?
So when you multiply, you look at the number with the lowest sig figs, so that one has 1.
Yeah. Yes. So 0.02 only has 1 sig fig. So in our answer, we have 1 sig fig, so that would be 0.9. Okay, I'm going to end the quiz in 30 seconds. Not everyone has submitted. I want to see, you all got the first 2 answers correct, but I want to see what you all put for the third one before we go over it. So I'll give you 30 seconds. Make sure yours are submitted. Okay. 5 more seconds. Okay. Okay, so in this third row, we have 2.14 plus 0.5559. How many sig figs do we have in our final answer? We have 3 in the final answer because we're adding, so we go to the least significant decimal place, which is right here. So we can go 2 decimal places past the 2. And then what's our final answer with rounding? What do you all think? Okay, I heard 2.70 and 2.7. So we do round up the 9 to be a 0. So we have 2.70. And we need to include the 0 to have the 3 sig figs. So remember, zeros past the decimal point are significant, so 2.70 is the answer there. Okay, sig figs in the last row. What do we think?
2.
Where do we get 2?
Because 4.5.
Because 4.5, yes. So in scientific notation, we look for the coefficient that's multiplied by 10. We have 2 sig figs here. We're multiplying, so we just care about number of sig figs. Here we have 3. 2 is less than 3, so we have 2 sig figs in the answer. Then how can I write this answer with this number with 2 sig figs? Great. Okay. I heard a few people say it. We use scientific notation, 2.2 times 10 to the 7. You could also write that number, but in science, we don't usually communicate in very large numbers written like this. We use scientific notation. Both answers answered this question correctly, but if you're asked for scientific notation, then you need that. Yeah.
For the second one, can you explain why it's 1?
Yes.
The only reason why I thought it was 2 was because it had a 0 and 2 behind the.
Yes. Okay. So, and I'm going to go back to the rules first. So this is an example like this one, the first one here, where we have a 0 to the left of a non-zero digit, and those are not significant. They don't communicate. Right. Zeros to the left of non-zero numbers don't count. If we were to write this in scientific notation, we'd have 5.04 times 10 to the negative third, and that would have 3 sig figs. So that number only has 3. We go back. The 0 is not significant. So it is 1. Okay. Yes.
I'm sorry, can you explain how the last one was 2 sig figs?
Yes. So why is this last one 2? So we're looking at 2 numbers here. One is in scientific notation, and one is not. That second number, 4.99, that has 3 sig figs. The first number, 4.5 times 10 to the 6, whenever we have scientific notation, everything that is multiplied by 10 is significant. So we have 4.5, that's 2 sig figs. Since we're doing multiplication, we just find lowest number of sig figs, and that's the number of sig figs for the answer. You're welcome. Let's see. Okay, for the next 2 slides, instead of going through them, I'll give you what these answers are, and then after class or in office hours or in recitation, try getting on your own to those answers with the correct number of sig figs. So the first one here is 236 grams. Second one is 1.115 milliliters. Then I'll go to the next page in a few seconds. On the next page, first one is 446 grams per meter cubed. And let's do this last one, but the formatting is off. This is 6.93 times 10 to the power of 3 centimeters cubed, and then divided by 30 centimeters. So try working that one out. We'll go over that and then we'll go to the next few slides. Yes.
For the top one, if you were to write it in scientific notation, it'd still be correct.
Yeah, you can still do that. As long as you have 4.46 power of 2. There are times when sig figs are used for 10 to the power of plus or minus 1, plus or minus 2. It's more common when the power is 3 or greater, or like -3 or smaller, I guess. Yeah. Okay, what did you all get for the value without considering sig figs? 231. Okay, so if you plug this into your calculator, you should get a value of 231. The units here are centimeters squared. We'll talk about dimensional analysis on Friday. That's because we have centimeters cubed divided by centimeters. When you do a division like that, you reduce the exponent by 1. Okay, so we have 231, but now we have to think about sig figs. How many sig figs are in this first number? 3. How do we know it's 3? Because there's 3 non-zeros. But yes, so the number that's multiplied by 10, 6.93, we have 3 non-zero numbers. And then how about for our second number? Is it 1 or is it 2? It's to the right, but there's no decimal. Yes, so let me go back to this again. It's an example like this where we have a trailing 0 without a decimal place, so that these zeros at the end are not significant. So in the value 30, just the 3 is significant. So this is only 1 sig fig. So our answer, 200. Or 2 times 10 squared, if you want to use scientific notation. But I was just telling some students, we often see scientific notation if the exponent is plus or minus 3, plus or minus 4, plus or minus 5, and so on. It is, you will still see when the power is 2 or -2 or 1 or -1, but it's less common. Okay, we will go on to the next slide here. I encourage you to try those earlier problems. Okay, so we've talked about measurements, but there are some values that are exact numbers, and we say exact numbers have no uncertainty, or they have an infinite number of significant figures. So an example is anything counted. If you're counting 5 pennies, you have 5 pennies. There's no debating any fraction of a penny there. So you can say you have 5.00000 on and on and on pennies. So we say that would be an exact number with an infinite number of significant figures. If you're counting number of atoms, since it's counted, that has no uncertainty, infinite number of significant figures. So we don't, when we're trying to identify how to reduce number of significant figures in a final calculation, we don't care about these significant figures because they have infinite. Other examples are equalities. So if you're converting from seconds to minutes or minutes to seconds and you're using this conversion in a calculation does not reduce your total significant figures to 1 because we have 1 minute or 60 seconds here. We say there are infinite number of significant figures, and so these don't reduce. Same thing with converting inches to centimeters, meters to kilometers, cups to quarts. All of those conversions are not considered in when determining number of sig figs. I'm going to skip the next slide and just run through these two before we're done. So all measurements require units. Typically, when we're communicating numbers in chemistry, we are communicating some sort of measurement that has to have a unit attached to it. But all measurements have some uncertainty. That's due to the limitations of the equipment and the limitations of the observer. So if you're using a ruler, that only has so many hash marks to tell you exactly when you're at 1.2 or 1.3 inches. Any more precise than that, so additional decimal places, would be an estimation. When we're communicating significant figures of measurements, all figures up to and including the first estimated figure is significant. So I have an example of this on the next slide. So we include that estimated figure. When you are measuring, we record all certain digits and then the first estimated. And then we say all of these, all certain digits, and the first estimated are significant. So here are 2 graduated cylinders with the same amount of liquid, of green liquid in them. In this first graduated cylinder, we know for sure we have 14, let's say these are milliliters. We know for sure we have 14 milliliters. And then we have to estimate between 14 and 15. So we have 14 with some decimal. I wrote 14.6 milliliters. So 14 is the certain digit and the 0.6 is the estimated. All 3 of these are significant. For this graduated cylinder, we know for certain we have 14.6 something. So the 14.6 now, because of all these hash lines, is significant, and we can estimate 1 more digit. So we have approximately 14.63 milliliters. We have 4 sig figs in this answer. So the more precise measurements come from the more precise instruments where you can measure to a smaller decimal place. Alrighty, I will end there. We'll continue on Friday.